All right, let's start with chapter 13, problem set number 3. First problem is 61. At what height above the Earth's surface is the energy required to lift a satellite to that height equal to the kinetic energy required for that satellite to stay in orbit at that height? Yikes. So let's look at the Earth real fast. Okay, so we're looking at the Earth. Now, the Earth has radius here, r. Okay. Now, what I'm going to do is I want to lift a satellite from the surface out to some height here. We call it h or whatever. That's the height that I want to lift it to. So I need to move this from here to here. How much energy does that take? And then if you get it here, and now it's in, let's say, circular orbit there, how much energy for the circular orbit? So there's two questions, and we're going to have to take them equally. So the first one is the energy required to lift the satellite. So basically what we're saying is the energy required equals the work done. And we know the work is the change in the energy. And in this case, we are changing the gravitational potential energy. So what is our gravitational potential energy formula? Well, we know UG is equal to negative GMM all over R. So that's our formula. So when it's at the surface, it's just GMM over R, and when it's at the height out here, it's going to be a different distance. So let's see how that works out. So I'm going to do change is going to be final minus initial. So this is going to be negative GMM over, what's my R value here? Well, it's R plus H, because it's R plus H. And then you do final minus initial, so minus a negative, which would be plus GMM all over, and it's just R, because the initial was at the surface. So this looks okay to me. One of the things about this that's important, though, is, do we know the mass of the Earth? Do we know the gravitation? Do we know the radius? Do we know the height? There's a lot of things we know here. So, and it says at what height. So we're going to have to eventually here solve for it. So this is our work done, our change in energy. So that's going to be important. Before we get too far into this, let's tackle the other side. So if our object is in circular orbit here, one thing I know, if you're in circular orbit, is that the centripetal force is the gravitational force. So I have mv squared over r is equal to g big M little m all over r squared. This time, this m and this m are the same, so they're going to magically disappear, and this r are the same, which is good. And so I end up with speed squared is equal to g big M over R. So that's the equation for the speed. Now it says equal to the kinetic energy required of the satellite to be in orbit. Well, what is our kinetic energy formula? If I remember correctly, my kinetic energy formula is equal to 1/2 mv squared. So I'm looking, I have a v squared here. So could I write my kinetic energy in terms of this? 1/2 m, and instead of v squared, could I just write now in this case though, this r here, I don't know how I got a big R here. What R are we talking about? We're talking about at this height. So little m. So now they're saying, at what height does this equal this? So if I simplify this and set it equal to this, I should be able to solve for h. So let's set them equal to each other and see what happens. I have these over here. That's equal to 1/2 Now, that's really interesting because I notice this is 1/2 GMM over R plus H. This is negative GMM over R plus H. I think those are like terms. And because they're like terms, I'm going to add this to both sides. So this is 1/2. This is 1. So if I add this to both sides, I end up with G big M little m all over R is equal to, this is 1. So 2 over 2 plus 1 over 2, or 1 plus 1/2 is 3/2. Which I think is cool. I can see that the GMM, now that I only have 2 terms, those cancel. And so I'm left with this 1 over R is equal to and so I'm going to do a little cross multiplication here. And I have 2 R plus H is equal to 3R. So I'm going to distribute, move my thing up here. So 2R plus 2H is equal to 3R, subtract. So the height in which this happens is going to be 1/2 of a radius. If we need to solve for a value here, we know that the radius of the Earth is 6.37 times 10 to the 6th. And if I divide that by 2, so 3.19 times 10 to the 6th meters. There's another part to this question here. It says, it says for greater heights, which is greater? The energy for lifting or the kinetic energy for orbiting? Well, one thing we see here is that as R gets bigger, speed goes down. And if speed goes down, the kinetic energy is going to go down, but it's going to take more energy to lift it. So at greater heights, the kinetic energy is less, but the gravitational energy is more. All right, let's move on to 63. An asteroid whose mass is 2 times 10 to the negative 4 times that of Earth revolves in circular orbit around the Sun at a distance that is twice the Earth's distance from the Sun. Calculate the period of the revolution of the asteroid in years. All right, let's write this stuff down. So it says the mass of the asteroid is equal to so 2 times 10 to the minus 4 times the mass of the Earth. And the orbital radius of the asteroid is 2 times the radius of the Earth. So it says calculate the period of revolution for the asteroid. So these two things are orbiting around the sun. And because these two things are orbiting around the sun, I know that Kepler's third law holds true. And it says that the t squared over r cubed ratio for everything orbiting the sun is a constant. So I can just set this up. I can say that the t squared for Earth divided by the r cubed for Earth is equal to the t squared for the asteroid divided by the r cubed for the asteroid. And then I'm going to write them in terms of the Earth. So left side, I still have the same thing. On the right side, I have the t squared for the asteroid, which is what I'm solving for. And here, it says I have 2, but you have to cube the whole thing. And that's where I think people make a little bit of a mistake here. So, if I expand and cross multiply, I end up with this expression here, 8 times t squared Earth is equal to t squared for the asteroid, because the r's disappeared. And that means that the t for the asteroid is going to be root 8 t for the Earth. And the square root of 8 is 2.8. And what's nice about this is they want it in years anyway. And because the t for the Earth in years is 1 year, this is years. The second part of the problem asks a completely different question. It says, what is the ratio of the kinetic energy of the asteroid to the kinetic energy of the Earth? So we have to start from a couple basic ideas here. And one of them is that if you're in circular orbit, let's say these planets are in close to circular orbit, because the centripetal force is equal to the gravitational force, and mv squared over r is equal to g big M little m all over r squared. I'm looking for the kinetic energy, and then we know that kinetic energy is equal to 1/2 mv squared. And so I'm seeing this over here. So in order to get this to look like that, I'm going to multiply both sides by r, and then multiply both sides by 1/2. So let's look over here. I'll come up here, it'll be a little easier. So I have mv squared over r is equal to gmm over r squared. If I multiply both sides by r, I end up with mv squared is equal to gmm all over r. And if I divide both sides by 2 or multiply both sides by 1/2, I end up with 1/2 mv squared is equal to 1/2 gmm all over r. And this is the kinetic energy. So I can actually use this idea. So the question says, what is the ratio of the kinetic energy of the asteroid to the kinetic energy of the Earth? So I'm going to do kinetic energy of the asteroid divided by the kinetic energy of the Earth. And I'm going to use this formula. So in each of these cases, this big M is the mass of the sun, because they're both orbiting around the sun. So this is the mass of the asteroid, this one's the mass of the Earth, this is the radius of the asteroid, this is the radius of the Earth. And we get a whole bunch of stuff to cancel. The halves go away, the G's go away, the big M's go away. And I'm left with the mass of the asteroid divided by the radius of the asteroid, all divided by the mass of Earth divided by the radius of the Earth. And again, if we're dividing a fraction by a fraction, really multiplying by the reciprocal. And so, what it tells me here is that the mass of the asteroid is 2 times 10 to the negative 4 times the mass of the Earth. And I know that the radius of the asteroid and so all the variables cancel, and I'm left with, I'll write it over here, 2 times 10 to the negative 4 divided by 2. There's the ratio. All right, let's look at problem 65. 65 says, a satellite in circular orbit around a satellite in a circular Earth orbit of radius r has area enclosed by the orbit. The area enclosed by the orbit depends on r squared. Determine how the following properties of a satellite depend on r. Okay, sorry, this is a little hard to understand. Let me draw this. So here's the Earth. Okay, so here's our Earth here. And it says a satellite is in circular Earth orbit of radius r. Okay. So our satellite is out here. And it says something funny that I don't really understand, but it says the area enclosed by the orbit. So area would be equal to pi r squared. Okay. So it says the area enclosed by the orbit depends on r squared. So what we're saying is we say it depends on. They're saying that A depends on r squared. We don't care about what the constants are. A depends on r squared. That's what they're saying. And it's determine how the following properties of a satellite depend on r. All right. So the first one, it says, let's talk about the period. All right, let's talk about the period. So one of the things we know is that the centripetal force is equal to the gravitational force. Little mv squared over r is equal to g big M little m all over r squared. V squared is equal to g big M over r. But v, remember, v is equal to 2 pi r over t. Therefore, if I plug this in here, I end up with 4 pi squared r squared over t squared is equal to g m over r. I'm gonna have to flip this around, but you can handle it here. I end up with t squared is equal to 4 pi squared r cubed all over g m. So then it says, how does the period depend on the radius? Well, I got to get period by itself, so I'm going to take the square root of both sides. This is all constant, but this is then the square root of r cubed, which means t depends on r to the 3 halves, which is 1.5. The second part says, what about the kinetic energy? All right, well, let's do kinetic energy. Kinetic energy is equal to 1/2 mv squared. But I have a term for v right here, so I'm going to plug that in. So v squared is equal to gm over r. So if I rewrite this, I have 1/2 g big M little m times 1 over r. So the kinetic energy depends on 1 over r, or r to the -1 power. And what about the last one? Oh, there's 2 more. Angular momentum. Well, if you look at any moment, we could say the satellite is a point particle. So the angular momentum is equal to r cross p, which is r mv sine theta. Luckily, the r vector would be here. And we notice that the r vector and the v vector are perpendicular. So that's 1. So what we're saying then is that L is directly proportional to R. More R gives you more L. And then I think we already did the speed here. If I look back at this one, I'll write it down here. So v is the square root of, so this means this would be, v is dependent upon 1 over the square root of r. You know, I made a slight mistake here. But this v here, this v goes with this. So I actually have to amend this. So let's keep going here. R m because I can't have a v here because it's dependent on that. So now I got a weird thing. So I got to square both sides. So L squared, R squared, M squared, G big M over R. And now you can see that one of these R's cancels. So L squared is equal to R M squared, G big M. If I square root now, so L is dependent upon root R. That's interesting. I didn't see that coming. Okay, that's it.